Hello everyone, welcome to Kinetics 3. Now if you remember, we talked about the big two, right? The big two in kinetics are concentration. You know, if you have more stuff per unit volume, more collisions per second amongst the reactants, faster rate, okay? Second big one is temperature. The faster they move, the more they hit together, collisions amongst the reactants, faster rate. So the last packet, we talked about the initial rate method, and that was the relationship between rate and concentration. We looked at the integrated rate law, which for first and second order reactions was the relationship between time and concentration. Okay, and I had a good chat today with a couple of students on the office hour, and we were talking about problems students sometimes have. And sometimes it's trying to figure out not so much how to do the problem, but which equation to use, right? So a little tip we kind of talked about was, read the question, make a list of the things they give you in the left margin, right? And if time is one of them, right, it's probably going to be an integrated rate law problem, okay? If it's a table of concentrations and rates, it's probably a, initial rates method, okay? So the trick is, make sure you kind of read the question twice and make sure you know what kind of question it is before kind of just plowing straight ahead, because the most problems come on tests with kinetics where people think it's a certain kind of question, it's actually another. Okay, so just make sure you're okay with what kind of question it is and then go from there. Okay, so back to kinetics 3, which is the temperature thing, right? Okay, so all the all the effects of temperature on rates. All right, so it's kind of a bit of a mouthful. Oh, before we get down there is an Excel assignment. If I remember, I'll link it from the web page. But if I forget to link it, just go to the class web page, and it just basically gives you an Excel sheet with blank columns, and you basically follow the instructions, and you're able to plot the graphs we'll talk about. So natural log versus reciprocal temperature, and you get a straight line. Okay, that's called an Arrhenius plot. So you need to practice that a little bit. Hopefully the lab this week, I think it is a temperature rate lab, CV, crystal violet reaction. So you will actually, I think, plot. So that's good. All right. So temperature and rate, and this is a bit of a mouthful. Transition state theory and the Arrhenius equation. That was the name of my band in college. I'm joking. Okay, so transition state theory and the Arrhenius equation. The Arrhenius equation is the math. Transition state theory is the kind of the process it describes, right? Okay, so remember, we talked about it way back in the first part of the topic here. Fruitful collisions, right? So reactants bump, and if they stick, that's called a fruitful collision. That kind of two things stuck together falls apart to make products, right? So it's how many fruitful collisions you have per second amongst reactants, which governs how fast you make products or how fast reactants disappear, which is rate of reaction, okay? So number of fruitful collisions per unit time is essentially what rate of a reaction actually is on the microscopic scale, right? So when we break down this transition state theory, right, we have to think, well, what factors on the microscopic level would result in a fruitful collision, two reactants bumping and sticking, right? And then question, because we're talking about temperature, is that related to temperature, yes or no, right? So you might want to give that a little thought for a minute. What factors you think would determine if two molecules bumping into each other would stick, and would that factor be in any way related to temperature, right? First one is an interesting one, right? So it's actually the energy of the collision. So energy of reactants. If you like a weak hit, they don't stick. A strong hit, they would stick, okay? So there's a certain minimum energy of collision that must be overcome for the atoms to stick or molecules to stick together. And if you think about it, that makes total sense, because what's on the outside of every atom and molecule? Bunch of electrons, right? And electrons are naturally repulsive. So things have elastic collisions normally, right? When they don't react, perfectly elastic collisions, they bounce off perfectly because electrons are repelling each other, right? Okay, so those outside electrons will repel, and normally things will just fly away from each other just through electrostatic repulsion. So that electrostatic repulsion has to be overcome. It's like trying to get two north poles of a magnet together, okay? Yeah, you can eventually, but you've got to overcome that force pushing them apart, right? Okay, so the energy of reactants, if you bang them together hard enough, we call that the impact force. Good chance they're going to stick, right? Okay, is that proportional to temperature? Yes. Okay, the hotter it is, the faster they move, the more energy they have. Okay, so we can kind of write ourselves a little point here. Must overcome electrostatic repulsion. Okay, and is that a variable? Yes. Okay, because the hotter it is, the faster they go, the more energy those reactants will have in a collision. Okay, so yeah, that's the big one. That's the that's the 600-pound gorilla, right? Is the impact force, right? So if the impact force is overcome, yeah, it's going to be fruitful, right? Probably. Okay, it's a factor. All right. Next one. Well, the next one is, if you think about it, we already talked about it in the last packet. It's the frequency of collisions, right? So just statistically, how often they bump together, there's kind of more chances of a fruitful hit, right? So frequency of collisions. Now that's interesting because we actually just talked about frequency of collisions in terms of, hey, if they're closer, they bump together more often. That's a concentration term, right? So we talked about it already, right? So when we increase concentration, we also increase frequency of collisions. Concentration goes up, frequency of collisions goes up, rate goes up. Okay. However, if you think about it, if I have two things at the same concentration, then I heat them up, yeah, there's more collisions per second. So the distance didn't change, but the speed did, right? So the frequency of collisions kind of goes hand in hand also with temperature, right? So is it proportional to temperature? Yes. Okay. Frequency. That's just right here. More is better. More collisions per second. That's going to increase your rate. Is it proportional to temperature, or is it related to temperature? Yes, okay, because they're moving faster, they hit each other more often. So it's both a concentration and a temperature thing, frequency of collisions. Okay, all right. Now the next one is completely random. It's the fraction of molecules in correct orientation. Now, if we're in the classroom, right, I'll do a silly demonstration where I attempted to leave the room, and I'd wander around the room bumping into the walls, right? So I'd have a bunch of collisions with the walls, and eventually I'd hit a space in the wall we call the door, and I'd have a fruitful collision with the door, and I'd leave the room, okay? So the bottom line is, when two molecules hit, that's one thing, but they got to hit in the right spots, right? So as we'll see later, if my product is maybe Cl2 as a gas, yeah, the chlorine on one molecule has to hit the chlorine on another for a chlorine-chlorine bond to form. So we call that, the correct orientation. So molecules are twisting and turning in space. They actually have to hit the right atoms on each molecule together during the collision for that bond to form, essentially, right? So that's just a fixed number, right? So it's it's a random thing. So the fraction of molecules in the correct orientation, that's not proportional to temperature, right? It's not, is it, right? I'll put temp because we don't want to confuse it with time. Okay, so there'll be some fixed fraction. Maybe it's 10%, 20%, whatever that fixed fraction is. During a collision, if you kind of look over 100 collisions, how many of them out of 100 are in the right spot when they hit? Maybe it was 10, maybe it was 20, 20%, whatever. Okay, that's a fixed number, not dependent on temperature. Okay, so the big two then are, which will pop out in the theory, the so-called energy of the reactants, and we have to overcome a certain amount of kind of electrostatic repulsion. As we saw later, that's called the activation energy. Okay, so if I overcome what's called the activation energy, I can get past that electrostatic repulsion. And then how often they bump together. So we've kind of seen that one before, but this activation one's kind of new. Okay, now they all play a part, so they all go into the theory. Okay, but this is the big one. Okay, number one is the big one, as we'll see when we do the math. Okay, so moving on, we have collision theory in a nutshell, right? So for a reaction to occur, the reactant molecules have to collide, obviously we know that to be true, right, with an energy that gets over that electrostatic repulsion. So with a value greater than some minimum, which is called the activation energy. Okay, they also have to have the correct spatial orientation. The more often this collision with a certain energy or higher happens with the correct orientation, the more often that happens, obviously, the faster the reaction. Okay, so that kind of weaves all three together. Okay, but on an individual level, on an individual collision level, it's about energy and orientation. Okay, and in that process, you know, statistically over many, many hits is your, we call it a frequency factor later, how often they hit. Okay, so remember, now so far, we've only talked about the relationship between rate and concentration as given by the integrated rate law we looked at, okay, last thing in the last packet, and the first thing, which was the initial rates method, okay. So the initial rates gave us the rate law equation, okay, and the variables are speed and concentration. There's no time variable in there, right? There's no temperature variable in here. Temperature's more important right now, right? So there's no nod to temperature in there, but wait a minute, how can that be? Because temperature does play a big part in speed, right? This is why we have refrigerators, right? A 10 or 20 degrees C change in temperature can spoil your food pretty quick. That's a reaction, yeah? So it turns out concentration isn't changed by temperature, so it must be K. K is only a constant at 25 degrees C. The value of K, and I'll show you a slide, hopefully I'm doing it right now if I can find one on the internet, right? The value of K is exponential with temperature, right? So when we think about keeping concentration fixed, rates proportional to K, higher the temperature, the higher the value of K, and as hopefully I'm showing you, it's an exponential relationship, okay? So really what we're doing when we do an experiment in kinetics and have temperature as a variable, we're really looking at the effects of temperature on K. And within K, we have these three factors we talked about. So let's just recap. There are three factors, right, to do with increasing the number of fruitful collisions, yeah? Activation energy, frequency of collisions, and a fixed fraction of the correct orientation. Those three variables go into our equation which defines how K changes with temperature. Okay, and that's called the Arrhenius equation, which we'll talk about. So, bottom line is, K is variant on temperature. That's why it's always recorded in the book at a fixed temperature, standard temperature 25. But say at 30, K might be 4 or 5 times bigger because it can really change quickly with temperature. Okay, all right, so how does increasing the temperature affect reaction rate? Well, always increases. Okay, because it affects 2 of the 3 variables as we've seen, okay? So more molecules with activation energy or higher, more collisions per second, okay? And we'll just write a few facts here. K is constant only at 25 degrees C. So standard temperature at which K is stated is 25 degrees C. If you don't, this is why we always record the temperature of an experiment, right? We try and keep it constant for initial rates or something, yeah? So if you noticed in the table for the initial rates experiment, temperature was quoted, it might have been 22, 23, 24, 25 degrees C, whatever it was, right? So we always write that in our experimental write-up because it's important to know at what temperature this all happened. It does stay constant through the experiment. If the temperature had changed through the experiment, it wouldn't have worked, right? Okay, so we have to keep a fixed temperature for our initial rates, and we write down what that temperature is. Now we're going to do experiments where we keep the concentrations fixed and change the temperature and look at rate. Okay, so if you increase the temperature, you will always increase the rate of reaction, more collisions per second, and as we'll see in a moment, more molecules moving faster, having that activation energy or higher. Okay, so K can change rapidly over small temperature changes or ranges, right? So over a small change in temperature, as we showed you hopefully with the plot there, K can change rapidly, therefore because K is proportional to rate of reaction changes rapidly over a small temperature change. Again, this is what we own fridges and freezers. Okay, so let's get into the nuts and bolts. So we know K is proportional to temperature, right? Somehow. We have to kind of break that down and rate is proportional to K. So when we're measuring temperature, rate's proportional to K, proportional to temperature, right? Okay, but it's not linear. It's important, right? So how do we model that non-linear behavior? Okay, so what we're going to do, we're going to break it up. So mathematically, K, that's our rate constant, remember? Rate constant. The same one from the, rate law equation, the same K, apart from now it's a variable. Now it's a variable because we're changing temperature, right? And we have those three things we talked about, right? So Z, or Z, right? Frequency of collisions. P is that kind of fixed fraction with the right orientation. And F, this is the one that's important. F is the big one. It's the fraction of molecules with the activation energy, we call it, or higher. So you have to get past that kind of initial repulsion force of electrostatics. If the impact has that energy or higher, it's the fraction of molecules in the sample with that. Okay, so that's F, fraction of molecules with EA or higher. And that's the big one. That's the, that's the main variable, as we'll see. All right, so moving forward then, we talked about it a little bit. Let's dig into some details. To what extent are those three, Z, P, and F, affected by temperature, right? Collision frequency, is that affected by temperature? Yes. Okay, so as you increase temperature, Z increases. Okay, so you increase the temperature, the number of collisions per second increases. So that's a, relationship between the two. It's important, yeah, so yeah. If you like, we talked about it down here. We talked about it last time as well. Okay. Reactant orientation, hey, we talked about it. It's just a fixed fraction. No effect. No effect, right? Okay. So the reaction, if the molecule's in the right spot when they hit, that is not affected by temperature, okay? And just to kind of, I'll show you, there's a slide here which is kind of small, all right? So I'll show you a better one, all right? I think this is actually in the back of the packet, right? If you want to look in the back of your packet, it's there. So here we have a microscopic look at a reaction, yeah? So we have that's N, NOCl, right? NOCl, NOCl. And those two molecules bump together to make two NOs. So that bond's going to break, right? So I'm going to get NO by itself, right? And then I make Cl2. So that one has to stick to that one. So if I'm thinking about colliding these molecules in my mind, what has to bump into what on the molecular scale to make a Cl-Cl bond? Well, the Cl ends have to bump together, don't they? So what's going to happen is the two Cl's of each molecule will bump together, form a bond, while simultaneously breaking a bond here and here. And that's called an activated complex. So if I was going to draw it real quick, right? So just for a split second, I'm going to get a Cl, an N, and an O stuck to a Cl, an N, and an O, right? Okay, so that bond's going to break, that one's going to break, and that bond's going to make. And I'm left with products, yeah? Kind of hard to see it there because I squeeze it in. More details on that later. So you make this kind of collection of atoms all for just a split second stuck together all at once, and then they fall apart. That's called an activated complex, right? It's like, it's when two cars collide, it's when they're all just like one big thing, right? Before they just, explode kind of thing, right? Okay, so what would a fruitful collision be? Well, I have to have the chlorine end hit the chlorine end, yeah? So if I look down here, nitrogen end hits nitrogen. Well, I don't make a nitrogen-nitrogen bond. That's no good. Ineffective collision, right? So maybe a third of them are that, right? So a third of them were like that. No good. Next one, well, maybe the chlorine hits the nitrogen end. Again, I have to have a chlorine hit a chlorine to make a bond, right? Again, no good. Finally, maybe a third of them are this way. Makes sense, right? Because there's kind of three possibilities shown. The chlorine hits the chlorine. It makes a bond. These guys break. This guy makes. And we get our products over here. Okay, so maybe 1 out of 3 collisions are effective. And again, that's a fixed fraction. A third in this case, maybe. Right? Okay. All right. So, similar thing here. In the one down here, we have the formation of CO2 and NO, between NO2 and CO, right? So I need to make a CO2, so the O has to hit the C, right? That's basically the correct orientation. These guys don't work here. So a similar kind of idea. And that, again, as we mentioned, you know, transition state theory, we're making that unstable collection of atoms just for a split second, where everything just for a split second is stuck together, right? That's called the transition state. Okay, so we bang reactors together with a certain energy or greater to overcome repulsion. They then make this kind of loose, kind of bonded, kind of massive molecule, if you like, containing all the atoms, which that massive molecule called a transition state then falls apart, or it's sometimes called an activated complex, falls apart to make our products, right? And we'll look more at the nature of the activated complex as we go. But it's like the activated complex, if you like, is a consequence of a fruitful collision. Just for a split second, everything's stuck together. Then it falls apart to make products. All right, so that's the two kind of easier ones, right? Or less important ones in terms of the math. Orientation, no effect. And then collision frequency, which has, you know, less an effect than the thing we're going to look at right now, okay? So the 600-pound gorilla is activation energy, yeah. Now, I showed you this video already, Q video, right, okay? When you break off in a game of pool and you put all that energy into a collection of 15 objects, right? So imagine the 15 balls on the pool table are a bunch of gas molecules in a jar, right? Okay. The pool table has just been given a bunch of energy from the break, and the jar of gas, right, rather, has a certain amount of energy depending on its ambient temperature, right? Now, when you look at the pool table, are all the balls moving around at exactly the same speed? No, they're not. When you break off, some are whizzing around real fast, some are real slow, and some are even stationary, right? So there's a distribution of speeds in any collection of molecules. We call that the Boltzmann distribution, okay? So do molecules of a compound have the same speed at, say, room temperature? No, there's a distribution. And it's called the Boltzmann distribution, okay? Boltzmann distribution is very, very famous, right? So if I look at the Boltzmann distribution, T1 and T2, in this case, T1 is less than T2, right? So that may be 5 degrees and 20 degrees C, right? Okay. And what do we see? We see an interesting exponential shape for the graph of the fraction of molecules in the sample, right? So maybe it's 1,000 molecules or something. What fraction of them have a certain energy or speed? And some graphs you see speed down here, some graphs you see energy. We'd like to use energy most of the time because we can actually draw a line in the sand, which is the actual activation energy you need to overcome for them to stick, right? Okay, so let's look. So if I look at the blue one, blue for cold, makes sense, genius, right? Okay, so we have, like, if I think of that kind of like the average, right? The average molecular speed or energy is lower than if I look at the red one, which is a higher temperature, which will be here, right? So that makes sense, right? There's a distribution of speeds, a bit like a bell curve. Some are at high energy, some are at low. And that distribution broadens out at higher temperature. Because if you think at higher temperature, yeah, well, some are still going to be at 0, but the maximum temperature is going to be higher now. The maximum energy is going to be higher. So it spreads out to the right here. Okay, fair enough. So same area under the curve. The area under the curve is the number of molecules, right? Okay. Now here's the thing. Here's the line in the sand, right? So here's EA. Remember, activation energy, molecules have to have activation energy to overcome electrostatic repulsion during that collision, yeah? If they don't have EA, there's no way they're going to stick because they'll just fly off through repulsion, right? So they have to overcome that repulsion, yeah? So, interesting, look, if you look at the lower temperature graph, the fraction of molecules with EA or higher is actually pretty small. Makes sense, right? A small fraction of the molecules at a low temperature have this higher energy or more, right? If I move the graph to the side, look at this here, right? A bigger fraction have EA or greater. And look at the area of the two graphs. That's not proportional, right? So the area of the graph under the red one is much bigger than the area of the graph under the blue one past EA. In English, a higher fraction of molecules in the hot gas have EA or greater than in the cold gas, right? Makes sense, yeah, because of the distribution of speeds. A greater, because the graphs move to the right for the hot one, there's a bigger area under the curve there. And all we've got to do is model the area, right? Because we're interested in how many molecules, what fraction of molecules have EA or greater, right? And that involves a little bit of calculus. All right, so bottom line is what we got. Well, I kind of told you as I was talking there, so hopefully, you could maybe rewind me or I could just paraphrase it again, right? So features of the graph: as the temperature increases, the fraction of molecules, i.e. the area under the curve past EA, the fraction of molecules with EA or greater increases significantly, okay? And there's an exponential relationship there, okay? So really what we're doing is we're modeling this line shape with temperature as a variable and EA as a constant. That's what we're going to do, all right? Okay. Now, I'll introduce it before I take a quick break because I'm nearly out of time here, okay? Due to the line shape, okay, so we have a weird line shape there, as we just talked about, right? Due to the line shape of the Boltzmann distribution, the fraction of molecules with EA has an exponential relationship. And it turns out that the fraction, remember F is the fraction with EA or greater. That's this area here, right? That's what we want, right? The fraction equals, obviously EA is in there, minus EA over RT. So temperature is the variable, but it's an exponential and EA is a constant. That's modeling the area under that graph, fraction of molecules with EA or greater. All right. Okay. Now, turns out that, remember, K equals ZPF, right? Turns out that the frequency factor here is literally the most important thing because it varies so quickly with temperature, yeah? So these are, well, the fraction of molecules in a fixed orientation doesn't change whatever, but the collision factor varies only slightly over small temperature changes. So these are essentially constant, right? So what we're going to do, and we'll say it here, we'll say A equals ZP. So we've got a new constant called the frequency factor, right? So over small temperature changes, the ZP won't really change much. So therefore, we can go back up here, K equals ZPF, right? K equals A, which is ZP, and F is E to the minus EA over RT. And in its simplest form, that is the Arrhenius equation, right? So there he is, Swedish, right? Okay, so Arrhenius, it relates K, which is proportional to rate, with temperature as a variable, to a frequency factor constant, E to the power of minus EA activation energy over RT. T is a variable. And if you think about it, if we know K from an experiment, we know temperature, we can figure out activation energies, which is a super, super, super important thing to know. Okay, so I've literally got 50 seconds left. I'm going to pause there, right? And having introduced Arrhenius, we're actually going to take a little break. I'll come back to the activated complex thing in just a second. Oh, we need to talk about activated complexes just a little bit before we go on and do some math with this. Okay, see you in a minute. Okay, so I'm back. Got my Brownian motion generator, aka a hot cup of tea. If you get that reference, send me an email. Okay, so back to it. We left it with kind of the pure form of the Arrhenius equation, and there's the man himself on a Swedish stamp. Okay, so remember, K now is not a constant, it's a variable, right? K at 25 degrees C is a constant because it's fixed temperature, and that's the one in the book, right? But if we change the temperature just a little bit, K can change wildly. If we keep concentration fixed, rate's proportional to K, okay? And we'll see later, when they say, hey, the rate was doubled, that really means K was doubled, right? So that's a little trick for later. All right, now before we turn this into something more user-friendly, we like to have linear equations, remember? Okay, let's just remind ourselves what an activated complex is, or a transition state. So activated complex, transition state, same thing, semantics, right? Okay, so what it is, it's that unstable grouping of atoms that form during a fruitful collision. So two things bump together, and just for a second they're this kind of larger collection of loosely bound atoms that then fall apart to make different things we call products, right? So reactants bump, make an activated complex which lives for a split second, falls apart to make products, okay? Now, There's our definition. All right. So let me actually show you a picture. Pictures are cool. All right. So here's a fruitful and a non-fruitful collision for a reaction. Yeah. Let's not worry too much about the ineffective collision. Yeah. Let's worry about the fruitful collision. So if I have my reactants, which are chlorine atoms and our favorite NaCl, yeah. If I want to make Cl2 and NO, yeah, obviously the chlorine's got to stick to the chlorine, yeah, during the collision. So making a bond here, break a bond here, make a bond here, yeah. But just for a split second, we have what we call the activated complex. So just for a split second, we have that molecule, right? That bond will form, that bond will break, and we'll get our products, yeah. So that thing right there is called the activated complex. Now it can be as a result of two things bumping together and sticking, or as we'll see in a molecular rearrangement in just a second, it can be a moiety. That's a great word, moiety, right? It can be a part of a molecule, a moiety, maybe rotating or moving, right? So it can be kind of a rearrangement of a molecule by itself, or what happens when you bump two molecules together, okay? See the rotation in a second. All right, so get that back out of the way. All right, so the activated complex or transition state is that kind of loose collection of loosely bound atoms that stays there just for a split second and falls apart to make products. Once it forms, it quickly decomposes, and you need that activation energy to make that activated complex, right? So only molecules with EA or greater collide and stick to make activated complexes. They then fall apart to make products. So if you think about it, if you think about the rate of reaction, I've kind of been lying to you all along. It's not about how often this happens, it's how often they bump and stick, right? Because it's all about how many activated complexes are made per second. And of course, an activated complex is the result of a fruitful collision. Not all collisions are fruitful. Some fraction are, some fraction stick. Make an activated complex, that falls apart to make products. Now here's that rotation one I showed you about, okay? I got a better picture, which I'll show you, if I can find it. Of course, asking me to find stuff on my desk is sometimes tricky. All right, oh, here we go, here it is. So, this is methyl isocyanide and methyl cyanide. This is a more stable molecule, right? This is a less stable molecule, but both are real molecules, yeah? So what this molecule likes to do, if you give it enough energy, it will literally rotate this CN group spatially, yeah? And it will kind of eventually, because it's, you know, you give it enough energy, it'll go like this. You give it some energy, it kind of starts to rock. You give it more energy, it starts to rock more. And it eventually gets to halfway. And once it's got to halfway, that's like the activated complex, and it just flips over, right? So that's what we see kind of in terms of energy here, yeah? So here's our reactant. Now this is an energy level, oh, not energy level, it's an enthalpy diagram. So remember, higher is less stable, lower is more stable, right? So that'll be a delta H like we see in thermochemistry, yeah? So minus delta H means more stable products. So the cyanide, if you like, in its correct orientation, is more stable, right? So that's delta H reaction, okay? However, why don't things just spontaneously turn into more stable things? Because there's an activation energy, yeah? So I have to take that, I have to loosen this bond with temperature or energy, so this group rotates, this moiety rotates. And when it gets to halfway, you know, then it's just over, isn't it, right? So that's the activated complex right there. Okay, so that's a molecular rearrangement with an activated complex, molecular rearrangement. It's, you know, so why don't, back to the point, why don't things naturally just rearrange themselves to make more stable things? Because they have to have that energy, right? So that's why when you turn on your stove, think about it. Think about this experiment, right? So remember back in the day when we had stoves and we had to light them with matches, right? You turn the stove on and the gas just comes out. It doesn't spontaneously light, right? Why is that? Because you have to give some of those molecules enough energy so when they collide, they stick, yeah? So the oxygen and the methane, given the energy from the flame, from the spark, will then hit, right? And then that reaction produces heat itself, so then it becomes self-sustaining. So we have to initiate reactions by providing energy oftentimes, lighting a fire, right? Because you give some molecules EA, and then once they react, delta H is minus, heat comes out, and that heat goes on to make the next one work, and you kind of get a self-sustaining process. So exothermic reactions are self-sustaining, combustion self-sustains, because you give the next generation of molecules or reactants, if you like, EA or greater to do the reaction. All right, so that's a molecular rearrangement. Okay, here's another. So the difference, the difference in height between the enthalpy of the reactants and the height of the hill is actually EA. So you have to, it's like rolling a rock up a hill, right? And when you get to the top of the hill, it just rolls down the other side. And past that point, that's your profit in terms of energy, yeah? So you have to overcome activation energy. We have this joke in our house because we're all scientists, right? Oh, the activation energy for that process is quite high, right? So that means no one wants to do it. Like, oh, ask my, they're listening, right? They're out there. I say, ask my teenagers to clean their room. The activation energy is pretty high for that. Okay. All right, it's currently running about 2 Mars bars. All right, so the activation energy is that hump of energy, if you like, you have to overcome to get a reaction started, and I already talked about your stove. All right, so back to it. Key fact, for a reaction to proceed, the reactants, the bumping molecules, have to have EA or greater for it to work. The amount of molecules with EA is, yes, back to the Arrhenius equation, governed by, modeled by the Arrhenius equation. All right, so that's where we left it. That's our pure form of the Arrhenius equation, right? Okay, now, we've got to turn that into a linear relationship, because if we've got a linear relationship, we'll plot a straight line, and this is your XL, right? Okay, so let's try and turn that into a linear relationship. Now remember the inverse function thing we did a little bit with the integrated rate law for first order. Base E, natural log is the inverse function. So if we kind of do something with a natural log, that'll get rid of the exponent, right? And that's what we want. We want to get rid of the exponent, right? So all I'm going to do is bring this down here, right? I'm going to take natural log of both sides. So ln k equals, all right, ln, I'll put it all in brackets to start. Right, okay. That equals, if you think, now remember, log of AB equals log A plus log B, remember that one, right? So that's, if you like, literally A and B, right? That equals natural log of A plus natural log of e to the minus EA over RT. Now, why do we do that? Because that's an inverse function, it's going to cancel. Therefore, ln k equals ln A minus EA, I'll put it over RT. There we go. Now, that's awesome, right? But it's not quite in the form of y equals mx plus b, is it? Okay. Think about it. What are our variables? Our variables are temperature, which is on the right now, so that we'll call that x, and k, or ln k, which is on the left. Okay, so if I rearrange that, therefore, ln k equals minus EA over R, and I'm going to separate those variables. Oh, there we go. Separate those variables out, right? So I've moved this, I'm switching positions, plus ln A, right? ln k minus EA over R times 1 over T plus ln A, yeah? That's, I've got it actually written down here, y equals mx plus b. So if I plot, let's think about that for a second, right? Natural log of k up the side, reciprocal of temperature along the bottom, I get a negative slope of minus EA over R. Okay, so if I take the slope, multiply it by R, that's EA. Fantastic. That's what we want, right? And the intercept is ln A, so that constant, right? So it's a constant. Wherever it hits the axis, that's that constant. All right. Now, as you remember, y equals mx plus b, fair enough, right? If I'm just interested in the slope of that line, if I have 2 points, right? x1, y1, x2, y2. I can, for a linear plot, I can use y2 minus y1 equals m, x2 minus x1. So that's the just like we did with rates before, right? We had two adjacent data points. That's kind of like taking two adjacent data points on a graph. That's kind of just the equation of the line for the graph, right? So this is better for plotted data. Okay, and I think one of your questions in your homework is actually plotting something like that. All right, so a couple of different ways we can do it. We can plot natural log versus 1 over t. The slope is EA over r. Or, you know, take 2 points on that line, y2 minus y1 equals m, x2 minus x1. All right, so the gross gradient from this one, or just look at 2 points, maybe from a data table. That'd be nice, right? You don't need to, if you think about it, you don't need to plot that one. So I'm going to move that. That's table. That's plotted. Got them mixed. That makes sense, yeah? Okay. All right. Now, this isn't actually what you see in the book, right? Because we don't like having a negative out front here. So if I just multiply through and collect terms, I get a nicer version of that equation, okay? Which we'll see on the next page. Actually, we'll see it in the data sheet. All right, actually, I'll write it on the next page, right? This is the preferred version, and we'll see why, right? So natural log of K2 over K1. So I go back here. K2 minus natural log of K1 is the same as natural log K2 over K1, right? K2 is always the bigger number. We'll see why in a moment. Okay, so bigger temperature is T2, bigger K is K2, right? And they're coupled, right? Okay. Now, if I want to get rid of this minus EA over R and make it a plus, I just multiply through and collect like terms. So basically what I'm going to do is change the sign and switch the order, right? So that equals positive EA over R, 1 over T1, careful, because I switched the order, minus 1 over T2. And that is the version from the data sheet. And it's a more convenient version to use, even though it's not as intuitive as that one, which is simply y2 minus y1 equals mx2 minus x1, right? It actually works better for plug and chug, and we'll see that in a moment. All right. Okay, so there's a better version of my graph. It's a natural log up the side, 1 over t on the bottom. It has to be in reciprocal Kelvin. The slope is minus E over r. So if I literally do rise over run, get a value, that's equal to EA divided by r, right? So if I multiply that slope by r, I get EA. Okay. Now, experimental data. Experimental data is actually pretty straightforward, yeah? Okay. We'll talk you through it, yeah? And we'll do some optional stuff. Now, if you have 2 points on the line, there they are, right? So that's K1, 1 over T1. That's K2, 1 over T2. All right. Okay. Got to be careful here. Got to be careful here. So the larger value is 2. I got those switched because actually it's a reciprocal. So they're getting smaller that way. Careful. That's K2, 1 over T2, K1, 1 over T1. If I look down here, that makes sense, yeah. So experiment 1, 2's a bigger number, 2's further up, right? Okay. Or for temperature, slightly more to the left because it gets smaller to the right. Okay. All right. Make sure that's 2, that's 1. Okay. All right. Now if I look down here, yeah, so there's data from 2 experiments. There's K and T. So we found the value of K, maybe doing initial rates of something at this temperature. We found the value of K at this temperature in Kelvin, yeah? We could just throw them into this equation, making sure we keep our 1s and 2s straight, with 2 being the larger value of K and temperature, right? Okay, we can just throw them in there and get an answer, yeah? But if you wanted, and it's a good exercise, if you wanted to just use the pure version, you would need to work out the natural logs of K and the reciprocal of temperature, right? So I left some room there. If you wish to use the other form, you can do that and fill in the spots, all right? Or you can just use these numbers here with the preferred equation from the data sheet. Okay, so let's go through it nice and slow. Okay, so this is a classic question, right? What is EA? So the whole point of this is to either plot a graph and then graphically find the slope. Slope is EA over R, multiply by R to get EA, right? Or use a table with two adjacent data points and use this thing here, okay? You can, if you wish, be more pure and use the natural log minus the natural log 1 over t, 1 over t, and you can fill in data here, if you wish. But this is literally all you need with the more user-friendly version. But if you're deriving from scratch, right, that's further along. Yeah, it's not the true y2 minus y1 m x2 minus x1 version. It's a more convenient version which allows us to use directly recorded data, right? So let's look at it. Two ways to do it, right? Graph or math. On a test, obviously, there's going to be some numbers in front of you, right? So we're going to do the math method first, right? Okay. So 1. Because we have a table of data, and an equation, we're going to use the math method. However, if we generated a graph in lab and it had fit a nice straight line and given us a slope, we'd just take the value for slope, multiply by R for EA, right? Okay. Start in the method. This one's going to be math, right? Assign variables. Exclamation point, asterisk, right? So the one downfall of this one is if you use it, you got to keep straight which are the bigger numbers and the smaller numbers. Now, if you think about it, right, when we have this fraction k2 over k1, we always want that to be at a number greater than 1, don't we, right? So k2 should always be bigger than k1, right? k2 should always be bigger than k1 because when we divide out, it gives us a number bigger than 1, not a fraction, yeah? And because K2 and T2 are coupled variables, K at that temperature, yeah? T2 needs to be bigger than T1, okay? So in each case, 2 needs to be bigger, right? So I look at my data set, well, that's actually true, isn't it? So we're happy down here because this data set's been labeled correctly. If they'd switched the numbers, we'd say to ourselves, well, we've got to assign the bigger number as number 2, right? But luckily the experiment, bigger K, higher temperature, that's what we want. So these numbers are good. We can call that K2, K1, T2, T1. So I can't really stress that enough. Where people mess up with this, and to be honest, if you flip the fraction, change the order, it will work, but it's more math, right? So make sure K2 is bigger than K1 and T2 is bigger than T1. All right, if we assign them correctly, it works very simply, okay? So all we're going to do, stick those numbers into the equation. We call it plug and chug in chemistry, in physics, because that's all they do. That's a joke. Insert and evaluate, right? And then once we got that, we can use our EA, find EA, right? We can use EA to find K at a different temperature, which was the follow-up question, okay? So what is EA? What is K at this new higher temperature, right? Okay. So let's think about it, right? So write the equation, ln K2 over K1 equals EA, now it's positive EA over R, switch the order, 1 over T1 minus 1 over T2, right? Where we flip back, I'm going to fold this over, I'll do some origami, right? All right. More origami. All right, so we've double checked. The bigger K is K2, the smaller K is K1. Bigger temperature is T2, smaller temperature is T1. We're just going to throw them in here, right? So pause me, throw them in. Let's see what we get. Okay. ln 2.14 times 10 to the minus 2 over 1.05 times 10 to the minus 3 equals EA. Now R is yeah, 0. No, oh, you've got to be careful here, right? Because we're dealing with energy, which is in joules, we have to use the metric version of gas constant, right, which is 8.31 joules per mole per Kelvin, right? So 8.31 under there, right? 1 over T1, 1 over 759 minus 1 over 836, and that's Kelvins underneath, so that's reciprocal Kelvin free unit. So Kelvins cancels. Energy is going to be in joules per mole, right? Now a log is just a number, yeah? Okay, so I want you to work it out, okay? So you get natural log of this number, which we can do it, right? 2.14 10 to the 2 minus divided by 1.05 10 to the minus equals 20.4 equals EA over 8.31 joules per mole per Kelvin, 1 over 759, 1 over 836. Log of 20, 3 equals EA over, yeah, etc., right? Oh, move that up for you. Okay. Now, when you get an answer, rearrange to find EA, and you'll find EA equals 206.5, and I'm changing it to kilojoules per mole, right? So it's going to be 2. So you'll get 2.06 times 10 to the 5 as an answer, yeah? But we always put energetic numbers, joules in kilojoules, right? So 2 times 10 to the 5 is 200 times 10 to the 3, 200 kilojoules, right? So work it through nice and slow. There's your setup, right? We're going to rearrange to make EA the subject. EA, because joules per mole per Kelvin for R will pop out in joules, 2 to the 5, turn it into kilojoules, 200 kilojoules. Okay, so hopefully that worked. Now, part 2, I haven't got room for it, so I'll kind of do it on the back here. All right, so part 2 is, let's go back to the question, K at 6.865. Okay, interesting. So if you think about it, what you can do, you can go back and make row 3, K3, 865, right? Now, we're going to have natural log of K3 over K, take your pick, 1, right, equals EA over R, 1 over T1, which is 759, 1 over 865. So that's T1, T3, K3, K1, right? Okay, 65, okay. So you know what EA is, 200.6 times 10 to the 3, right? R, 8.31. What you're going to do, you're going to find, if you think about it, you'll get a value for ln K3 over K1, which was given, right, which was 1.05, equals 200.6 times 10 to the 3 over 8.3. I'm, you know, a bit loose with the joules per mole per Kelvin. 1 over 759 Kelvin, 1 over 865 Kelvin, okay? Now, important, right? Remember, logs divided are logs minus, right? So natural log of K3 minus natural log of 1.05 times 10 to the minus 3 equals all this, right? Oh, sorry, have a go. So work out, take this over, it's just a number, right? So take the natural log now or later, it doesn't matter. Okay, take it over, work out all these, yeah, work out all these, subtract the natural log of that number, and you'll get a value, right? Okay, now, how do you get rid of natural logs? It's e, right? So e to that value equals k3. All right, now think about it, right? How do you know if you're on the right track? Well, if you look down here, K obviously is getting bigger as temperature goes up. It's a little bit higher, so it's probably going to be somewhere in the mid 10 to the minus 2s. Okay, mid 10 to the minus 2s. And if you got it right, it's 5.8 times 10 to the minus 2. Let's make this worth extra credit, okay? So I've kind of given you a game plan there. Work out K3. I want you to kind of work through it. It's not hard math, it's just rearranging, yeah? But you're doing something weird, yeah? So you found EA from the previous part. You know these values, and it's nice to stick in a new row in the table here. Okay, all right. Once you've got that row, use that information with either the first row or the second row. It doesn't matter, right? Because they're coupled variables, right? And, you know, isolate natural log of K3 and then find K3. Okay, again, 5.8 times 10 to the minus 2. Just a number. K is unitless because, you know, when we use logs and exponents, units don't really apply. Okay. Now, I'm nearly at the end of my time, but I will tell you the trick, right? Okay. So, we're trying to find the activation energy for this process, yeah? Okay, so we have a certain reaction, okay? The rate of a particular reaction is quadrupled. So rate times 4. Here's a massive clue, 4 to 1. Okay, so because the rate increased by a factor of 4, if it was 1 mole per litre per second before, it's now 4 moles per litre per second, 2, 8, doesn't matter, the units are irrelevant, it's just a factor of 4 bigger, right? Now rate, remember, is proportional to K, so this is the big trick, right? So, natural log of K2 over K1 equals EA over R 1 over T1 minus 1 over T2. Fair enough, but this, hey, K2 is 4 times faster than K1. Remember, K is proportional to rate, right? So in the second example, 60 degrees C, only 5 degrees hotter, it's 4 times faster. That's okay. I'm going to run out of time any second. All you do, natural log of 4 over 1 is just a natural log of 4 equals, and you can put in the numbers, okay? So I'll be back in a second. All right, back again. Got a bit excited there, right? So here's the trick. Now just remember, so obviously you're going to put these temperatures in Kelvin, yeah? So the higher temperature is going to be T2, and the lower temperature is going to be T1, because remember, K2, T2, we want this to be a number bigger than 1, so K2 has to be bigger than K1. So hey, rate's proportional to K. If the rate's 4 times bigger, K2's 4 times bigger than K1, and that's what we're going to do down here, okay? So instead of writing the actual values for K, we only need their ratio. All right. So then we can put in EA over R, 1 over T1, which will be 55 in Kelvin, 1 over T2, 60 in Kelvin. Work it through. Okay, you should get 250 kilojoules per mole. Okay, try it. I'm super generous, right? Take a picture of your notes, all right? If you work it through and you get 250 kilojoules per mole, you're good. Now, that's a standard trick, right? Sometimes they might say, what activation energy is there for a reaction that rate is quadrupled when the temperature goes up? So they can just reword this, right? So they can make this fraction the subject. So when they want how many times faster, that's just the ratio of these two K's, right? Okay. Or they can ask you to work out EA given that ratio. That's the one we just did. Okay, so be careful for that. Wherever you see rate is quadrupled and it's temperature dependent, or rate goes up by a factor of 10 and it's temperature dependent, you're really talking about this ratio. So up by 10 is 10 to 1. Up by 5, 5 to 1. Hopefully that makes sense, right? Okay. Now, real quick, I think before we go on to the next section, there is, yeah, there it is. And we'll do this one. Okay? So I've given you a couple to kind of just confirm your comfort level, I guess, right? Okay. But in the back of the packet, here we have a question which relates to that whole, fraction thing with k, right? So let's read it and then think about it, right? So I'll work it through with you. Okay, so what you can do, you can kind of read through it with me and then try it, or just watch me do it, whatever, right? But think about it, right? So the activation energy for a certain reaction, EA, is given 65.7. Now instead of writing kilojoules, I'm going to write times 10 to the 3 joules per mole. Why did I do that? Because remember, I'm dividing by R. 8.31 joules per mole per Kelvin, right? Okay, so consistent units. And when people make mistakes on this, they can be off by a factor of 1,000 because they forget to do this. Joules has to cancel with joules. Kilojoules and joules don't cancel. Joules and joules do, right? Okay, and then T. Well, let's think about it. T2 is the big one. T1 is the small one. Okay, so T1 equals 0 degrees C, 273 Kelvin. T2 is the big one, 323, I think that's right. Add 50 to 273, yep. Okay, fair enough. So there's our variables defined, right, and constant. So natural log of K2 over K1 equals EA over R 1 over T1 minus 1 over T2. Fair enough, right? And we've got our variables here. Now, how many times faster? How many times faster means what's the ratio of K2 to K1? So this is what we want, right? We want to find the ratio of K2 to K1, and we'll show you this at the end, right? So we stick the numbers in. ln K2 over K1 equals, actually I'm just going to do the algebraic way just for fun, right? K2 over K1 equals 1 equals, now get rid of logs both sides, right? E to all that, EA over R 1 over T1 minus 1 over T2. That's true, isn't it? Because I did the natural log of both sides, right? If you like, E natural log both sides, right? Okay, so that's true, all right? Now I'm just going to stick numbers in. E to the EA, 65.7 times 10 to the 3. I'll leave units because it's raised up to the power, 8.31 joules per mole per Kelvin. 1 over T1, 273. 1 over 323. Okay, which equals approximately 88, right? Oh, sorry, there we go, right? So just to recap, we want the ratio of K2 to K1, which is really the factor by which it goes faster at the newer temperature, right? Get rid of the natural log by doing an E, do E both sides. Stick in the values, I get a factor of 88. Interesting, it's 88 times faster, right? But you've got to say that, right? That, I've told you that, right? I've told you the ratio of K2 to K1 is 88. I haven't told you how many times faster yet, so it's a bit like that whole finishing off the boiling point thing, right? Therefore, reaction is 88 times faster. You've got to finish with that because you've told me a mathematical fact here, and that's the interpretation of that fact there, right? So it's, it's the same number. Yeah, I know, it's the same number, but it's actually representing something we need. Okay. All right, so that's that one. Now, back to our last little bit of the packet, okay? So this is kind of interesting, okay? This is kind of it's interesting. Okay, let's take a look at it. So What we're going to start to talk about now is reaction mechanisms, right? So we kind of talked about this a little bit when we talked about activated complexes. So molecules bump, they stick for a second, and then they fall apart to make products. And we can kind of get an idea by the nature of the products and the nature of the reactants. Well, what must that activated complex look like, right? Because, you know, in that one example, the chlorine end must hit the chlorine end to make a chlorine-chlorine bond to make the product, which is Cl2, okay? So a reaction mechanism is either if it's a single step, right? Okay, if it's just one bang, right, one hit, it's simple, right? But sometimes reaction mechanisms are multiple steps, so we can't really predict a multiple step reaction, yeah? We can only kind of predict the kind of individual steps and then combine them, if that makes sense, okay? So let's just read through this one, okay? So reaction mechanism is a combination of what we call elementary steps. An elementary step is just a hit, right? So a hit, right? Okay, so an elementary step is a hit. It may involve two things, three things, or sometimes one thing just falling apart, right? So the elementary step is the actual fundamental process, right? A hit or a fall apart, one thing, two things, three things, right? Okay, so for example here, we have NO plus O3, bangs together to make this activated complex, and that's the symbol for activated complex, which is kind of weird. It kind of looks like that, okay? And that falls apart to make products, all right? So if I'm going to draw that, there's N and O and O3. Yeah, I mean, we're making NO2, right? So that bond's going to, if I just draw that properly, right? So I'll draw it up here. So NO, O, that's going to bump into there, make an activated complex, and that's oxygen. That bond will break, that bond will make, and we get these products. Okay, so there's our activated complex. It's not written kind of in terms of the geography of what it is, just kind of its formula, all right? But the oxygen, if you think about it, has to hit the nitrogen to make a nitrogen, oxygen, nitrogen bond there, NO2. All right, so there's our process. It's bimolecular. So it's bimolecular, meaning there's two molecules involved. So two molecules bump together, bimolecular. Elementary step, simple process, they hit, right? The molecularity of two means there are two molecules involved. So bimolecular, molecularity, same thing, okay? So we have a bimolecular elementary step. That's just saying two things hitting together, okay? If I had a unimolecular elementary step, it would just be one thing like we saw earlier with the rotating CN group in that one molecule. That's a unimolecular elementary step, just the rotation, the rearrangement of a molecule is unimolecular. Radioactive decay. An atom falls apart, right? Just the atom there and it falls apart. So it's one atom falls apart, unimolecular. So all radioactive decays are uni, right? Two things bumping together are bi. Three things, kind of rare, but if you think about it, three things could bump together to make something. An activated complex, that's our ter. We don't say tri, we say ter, all right? All right, so as you mentioned, some reactions feature unimolecular, that rotation, the isomerization, just changing shape of a molecule, nuclear decay, one atom, okay? Or rarely, three things. Now, why rarely? We mentioned this kind of earlier in the packet. If you think about it, if you're trying to have three molecules all meet at the same point in time and space with the correct orientation, that's kind of rare, okay? So, you know, a termolecular elementary step where three things have to hit is very, very rare. And if that was part of the reaction mechanism, the reaction would probably be very, very slow because that's what we call a slow step, right? Okay, so that's your basic vocabulary. Molecularity, uni, bi, or ter, one thing, two things, or three things, having a elementary step, either a falling apart for one or a collision for two or three. Okay, now, this is where it gets interesting, right? Because I kind of sort of lied to you earlier but didn't, okay? If it's a very, very simple one-step reaction, just two things bumping together, one thing falling apart, there's a definite relationship between what happens on the microscopic level with stoichiometry and what happens with the rate law equation, okay? So let's look here. Creative origami again, right? So, unimolecular, so just one thing falls apart, right? The rate equals Ka to the first power, interesting. This is what I want to take you away. I've got one thing and it's an A over here. I've got A to the first power here. If that's a single elementary step, watch what happens. If I have A bumps into A to make products, right? Whatever that product is, I got two A's, right? So it's bimolecular because there's two A's bumping together, like a classic reaction, right? And then because there's two A's as reactants, right? Oh look, it's actually second order with respect to A over here. So 1A as a product, sorry, 1A as a reactant, first order with A. Two A's, second order with A. Getting a correlation there. Let's see if you can predict the next one, right? So, creative origami again. A plus B makes products. So there's two reactants, A and B. There's one A and one B, if you like. So what do you predict for the rate law equation? If you got A to the first, B to the first, you're correct. So the molecularity is matching the order, isn't it, right? Molecularity is matching the order, but this only works for simple one elementary step reactions, okay? Remember, multiple steps are included in a lot of reactions, so this doesn't work, all right? So we can't assume this to be true ever. We have to do an experiment, which we'll get into in a second. Let's keep with the origami. Oh, kind of gave it away. So there's a term molecular, right? So imagine three A's all coming together at the same time, same place, right? What we're going to get? A to the third. Two A's in the B. What do you think? Two A's in the B. Second order with respect to A, first order with respect to B. And finally, ABC. A to the first, B to the first, C to the first. Again. Talk about it on the next page, but be very, very careful, okay? Don't assume this ever, because it's not true for multi-step reactions. It's true for single-step reactions, but not multi-step reactions. Most interesting reactions are multi-step. Okay, so we can write it in. What correlation did we just see? Okay, so the molecularity of a simple one elementary step reaction. So if you just have a couple of things bumped together and that's it, it's a single elementary step, right? Three things bumped together, that's it. Even though it's like A to the third, it's just one event, right? So if I have a simple one elementary step reaction, what do we saw? Order with respect to reactant equals, let's call it molecularity, right? So the number of individual reactant. So two A's would be A squared, one B would be B to the first, as we saw on the previous page. Okay, so hopefully that makes sense. The molecularity of a simple reaction, a one-step reaction, an elementary step of one, right? The order is the same as the molecularity. So there's two A's, it's A squared, one B, B to the first. Got it. Okay. But now the danger thing, right? Never assume this to be true. Danger, danger, Will Robinson, one of my favorite things, right?
Danger, Will Robinson, danger!
Never assume this to be true because often it isn't, right? So you will predict the rate law equation based on the stoichiometry of a reaction and it'll be absolutely wrong because there's more going on behind the curtain than you realize, okay? So let's look at a time where that must happen. So we must do initial rates experiments to find orders. Right, you can't just look. Okay. All right, so now here's a multi-step reaction. Okay, so most reactions, to be honest, are multi-step, yeah? So we have this reaction, right? So the formation of NO and CO2 from NO2 and CO. So NO2 plus CO turns into N, oh, we get NO3, no, wait. NO and CO2, NO and CO2. All right, so just basically swapping an oxygen between the two, right? That's what it looks like. It looks like these two things bump together and make these two things, right? So you may assume, incorrectly, what? Rate equals K, NO to the 1, CO to to the 1. You may assume that, and that's absolutely wrong because it's not a one-step reaction. It's actually a two-step reaction, yeah? So what we actually find out is this. So we have elementary step number 1, which involves two NO2s bumping together and forming NO3 and NO. And that process is quite rare, it turns out, or hard to achieve for various reasons we talked about, right? So maybe it's a high activation energy, maybe it's an orientation issue, whatever it is, right? If it's kind of more difficult to achieve for whatever reason, it's slower in terms of rate. So those fruitful collisions happen less often, and that's slow, yeah? And what you're doing is you're making these two things, yeah? Now once you've made NO3, because NO2 is a product, right? NO3 then goes away and reacts with the CO very fast to make our other product, right? Okay, there it is, yeah? So there are two steps in this process. It's elementary step number 1, NO2 bumps into NO2 to make these products. Once we've made NO3, it then goes on in a second step to make with CO, NO2 and CO2, right? And just like we did with, Hess's law, we're going to combine equations, yeah? So when you combine left and right, you get this, yeah? And as you know, you can just cancel like terms, right? What else you got? NO3, NO3. NO2 plus CO turns into NO plus CO2. That's our equation, yeah? What's that itch? Algebra. Net reaction. NO2 plus CO2 turns into NO plus CO2. Now, it's not written down anywhere, but if I was to guess what the rate law equation for this one was, I just look up here. This is a fast reaction. That's not going to determine the overall rate of equation because I'm making something real fast, it just off it goes, right? It's a bit like, here's my analogy down here, right? So when you have a multi-step reaction, the whole process is only as fast as its slowest step. That makes sense, right? So it's a guy working in the pizza shop, right? So my analogy is, the production line is only as fast as its slowest person. So, quit showing off, Frank. We got to get the pies in the oven because Frank's there just messing around, right? You're not going to get the pie out until Frank's finished because he's what we call the rate determining step, right? Or the rate limiting step. Okay, so a rate limiting step, you're only as slow as your slowest member, if you like, okay? That governs the speed of the reaction overall. So for a multi-step reaction, you're limited in speed by your slowest step. So if I look here, this is the slowest step, right? So because that's the slowest step, it's the one that counts, right? So I've got these two reactions. So I'm going to say rate is probably this. If we did the experiment, I'm going to bet most of my current salary is this, right? Because this elementary step is the slow one, right? That's the rate determining step. There's two NOs bumping into each other, bimolecular. This is the elementary step that's important because it's slow. That's probably going to be the rate expression or the rate equation. That makes sense, yeah? So when we actually do the initial rates, we can kind of almost work backwards and say, well, that must have been the slowest step. And if we can kind of do this math up here, we can kind of see why. Okay, neat. Now, talk a little bit about catalysts. Now, for better or for worse, when I was in graduate school, I was actually in a surface science research group, which actually looks at this stuff in some detail, right? So catalysts work, yes, as we saw earlier, by creating a higher local concentration, flat surface versus three-dimensional volume, right? We talked about that a little bit. But there's also an energy component, right? Okay, so if we look at what a catalyst actually does, okay, now we've got to be careful how we say this, okay, so here's an energy level diagram. So I'm bumping O3 into O, and I'm making, that's written wrong, isn't it? O2 and O2, right? Okay, so it's going to be a simple bimolecular elementary step. Just these two things bumping together. We're going to make a transition state, there's ozone and there's the other oxygen, right? That thing. And then it's going to fall apart to make products, yeah? If I just bang them together in the gas phase, that's the energy it takes to overcome, that's the activation energy. That's the energy it takes to overcome the electrostatic repulsion. However, if I put a catalyst in there, like a surface where they can meet, something like that, and this is the thing, this is where I got into a knockdown, drag-out fight with one of my professors, right? So I was a chemistry 102 teacher at the time, TA, right? And I'll tell you the name of the professor because she's retired, Sharon Fetzer, right? She was like, a catalyst lowers the activation energy for a reaction. I'm like, no, it doesn't. It gives an alternative pathway. You can't lower the activation energy, right? That's like breaking the rules of thermodynamics, right? But you can, if you look here, provide a different pathway where that plus that, yeah, it equals the gap, right? So it's like I've gone over a little hump and then over a little hump, but together they're the same height as the activation energy. I've provided a different pathway with two or more, well, you know, more steps, right? And each step has a lower individual activation energy, right? So the total activation energy is the same, just I split it into two parts. Now, if you think about it, because there's a fixed fraction of molecules with EA or greater going to react, because activation energy is essentially now lower, I'm going to say pseudo lower, right? It's actually the same energy, but I've provided a pathway where it looks lower, more of them will react, yeah? And that's what a catalyst does. It provides, and here's the phrase we like to use, right? You know, to a layperson, Sharon Fetzer, it lowers the activation energy. To an intelligent person, it provides an alternate reaction pathway where the sum of the activation energies for the steps equal the total. Okay? And because neither of the steps is very high, more molecules will have that step energy, if you like. Okay? All right. So that's how catalysts work, all right? They provide an alternate reaction pathway with the individual steps having smaller activation energies than just the bumping them together. Okay, all right. So if we look at what happens in that exhaust of your car, there are literally half a dozen little reactions, right? And all of those little reactions, the energy it takes to stick to a surface, the energy it takes for a molecule to dissociate on the surface, to roll around on the surface, all those add up to the molecule sitting in the gas as an activation energy. All right? So catalysts in cars are super efficient because, you know, they effectively make it a much lower barrier, right? Okay, that makes sense. Do a similar thing in a test tube. It's just that the molecule, you know, we might stick an H plus on something. So I have H2, O2. H plus is a catalyst. Maybe H plus just sticks on there, makes the molecule unstable, less stable, more reactive. So it's just, you know, it's just like a hitchhiker. So H plus is often a catalytic hitchhiker. I think I'm going to patent that. Catalytic hitchhiker. Okay, heard it here first. All right, so that's like the end of the packet. All right. Yep, we just had the questions. So stop there. Okay. Any questions? You know, usual thing, office hours and water cooler chat and discussion. I was actually pleased to see a couple of students at office hour and we had a good chat today, actually. So that was earlier today. So I'm putting this together on Thursday afternoon. So yeah, I mean, feel free. Office hour, discussion. All right, stop there. I'll see you guys next time.